Honestly, I didn't have a chance to prepare this lecture. I have a really full day. This is my second lecture of the day, and right after this, I'm going over the hill to eBay to give a talk, and then I'm coming back over the hill again because I have to be back here at 9 a.m. tomorrow. So I'm really tired, but I know this stuff, so don't worry about it. Thanks for really but what I want to do is kind of like zoom out and starlight consensus. Like we're done, let's wrap it up, put it in context, talk in a little bit more detail, but not excruciating detail because it's really a grad student topic of the big impossibility result in security, the so-called Fisher-Lynch-Patterson impossibility result, which establishes some important impossibility results around consensus itself. We talked about it informally. I'm going to give you the definition of what it tells us so that you know it. It's important to know. Without getting into the details about how they proved it to be the case, because that's really fussy stuff. The paper that proves the result is one of the most beautiful pieces of computer science writing I've ever read. Like, it's gorgeous. But it takes like a week to read it, you know? So I'm not going to make it all. And then I'm going to talk about, Multi-Paxos, all the pieces, reflect a little bit about Raft as an alternative, and then we're going to walk away from consensus. Consensus is done, except I imagine it's going to be a subject you're going to want to talk about all the way up until the final in-office hours as we drill these various infinitely many what can go wrong in Paxos scenarios. But then I want to start to make a pretty significant shift. Remember, I said there were these modules, right, in the class. It was like time and asynchrony, and there was fault tolerance. And at some level, we've dispatched with time and fault tolerance. We've talked about them. There's two things left to do that. Talk about sort of consistency, which up until now, we've sort of just talked about as this binary thing. You're either like strongly consistent, which means you look like you're not distributed, or you're not. And we're going to look at this as a much more nuanced thing. There's lots of different versions of what it means to be consistent. As you would intuit, as is the case like with delivery protocols, different consistency guarantees have different costs. So a lot of times this is a game of navigating trade-offs and saying, what kind of consistency does my system need? How much am I willing to pay? And so starting today, we're going to start looking at defining versions of consistency, both that are considerably weaker than what we call strong consistency, as well as versions of consistency that are actually stronger than what we call strong consistency. In particular, the idea of like serializability of multi-key transactions. Okay. And then of course, finally, now how does this, time, it's sort of, we talk about time first because there's this sort of fundamental uncertainty around time that makes distributed systems look different than the other systems we might have programmed. We look at this issue of like, when you admit that loss can happen in your model, how do you work around loss? What are various protocols that you can come up with that achieve some level of redundancy, right? That's what we've been talking about for some time. And then, but this kind of dovetails really nicely into, in general, in a world in which, for example, computers may crash, messages may be lost. You do things more than once. You have more than one copy of the data, and more than one version of the message. And as soon as you have more than one thing that are supposed to be the same thing, that directly gives rise to concerns about consistency, right? If I only have one thing, it's consistent by definition. If I have two copies of the same data, they're only consistent if they agree. So in some sense, when you solve the FT problem, you create the consistency challenge. You buy that? Like these two things are very closely tied. And then once we've gotten through all of that, the very last thing we're going to do is, gee whiz, these are the three reasons why it sucks to do distributed systems, we should never do them. And then it's like, oh, but by the way, if you do them right, you can go fast. And then at the end of the talk, we're going to look at some of the ways in which, if you solve all three of these issues, you can go fast, and that's great. Yeah? That's kind of this is what, you are here, and we're about to come down into here, and it's going to get fun. Okay.
Just 150.
Yeah. Questions? Consensus potpourri. So, I taught you this really simple gadget that implements consensus. And I started by calling it Paxos, but then I came clean and said, okay, it's not really Paxos. It's this like mini protocol called the Synod protocol. It has these well-defined properties. Right? That was the first thing we studied, this 2-round protocol that does reconnaissance, does a prepare phase, does an accept phase. We studied this in excruciating detail, right? We spent like 2 days on it. And then I said, okay, that's all well and good, but a gadget that just, decides one thing and then never does anything ever again is not useful. It was just a theoretical problem. How many angels can dance on the head of a pin or something like that? If we want to make a practical system, we really need to instantiate some kind of gadget that allows us to make a totally ordered set of operations, totally ordered log of operations. And we looked at some use cases for that. One might be that, I don't know, you want to have a sequence of transactions so that every element in the sequence depends on all the things behind it. That's sort of the cryptocurrency use case. But more commonly than that, you're doing something like state machine replication. You want to have this world in which, okay, I have these different computers that are supposed to be replicas of each other. Now, I could do primary backup replication, I could do chain replication, or I could come up with some way to have a bunch of computers running Paxos, or actually, I guess these computers are all running Paxos, to determine a totally ordered log with the property that everybody has the same totally ordered log at the end of the day. Because if everybody has the same totally ordered log at the end of the day, everybody who has a state machine can just play the transitions in the log, and we'll have a guarantee that all these state machines always agree. Like, so that's great. That's kind of like, that's the killer use case for things like protocols that give us a totally ordered log. So I said, okay, well, if we want to take Synoff and turn it into a protocol that gives you a totally ordered log, you can, but there's like a number of retrofits that you need to do to it. Does anybody remember what the tricks we had to play to turn this toy protocol, right? And remember, it's a protocol that looks like, hey, will you prepare my thing? Yes, I will. Hey, will you accept my thing? Sure, I will, in the happy case. Right, that's Synoff. What do we have to do to Synoff to make it a practical way to implement an ordered log? Yeah?
Add in like an index number?
Yeah, so like number one, you're absolutely right. The easiest sort of retrofit is to say, we're going to like extend the API. And I think we convinced ourselves we didn't really need to change the API of the prepare call. We just needed to like extend the API of the accept call to include like, in addition to everything else, which of these slots are you talking about? I'm talking about slot number 2, kind of thing. Okay, yeah, what else? And that would work, right? Like, if all I did was change the API to include a number, that would mostly work, but it wouldn't be practical. Yeah?
Also add some sort of leader designation so that there's one node that proposes most of the time.
That's great. And that's exactly the right way to think about it. It's like, we want a best effort. I'm actually going to write that. Because in general, we couldn't say we need perfect leader election, because perfect leader election requires consensus. So we can't say in order to implement consensus, you need to have already implemented consensus. That wouldn't work. So, but what we can do is we can use like a best effort leader election protocol to make it extremely unlikely that we have 2 leaders for a long time. Okay, now why was it so important in the context of Multi-Paxos for there to just be 1 leader? I thought the fact that there could be many proposers was a feature of Paxos. Yeah?
You can only prepare once if that's the case. Or
Well, there's an optimization that we haven't said that contextualizes what you just said. So what is the other thing we've done to Paxos to make it multi-Paxos that makes us care so much about skipping that, about skipping communication? Yeah.
If we, a proposer, want to propose slots, not just 0, but also 1, 2, 3, 4, and 5, please skip the prepare phase for every slot.
Exactly. So the intuition is like, what is the prepare phase? The prepare phase is when you go, hey, everybody, who wants to follow me? You know? And if enough people say, I'll follow you, then you know you can ask them to do things, too. Right? The intuition is, if I have a whole bunch of people who have agreed to follow me, and have agreed to ignore any request from law over the mine, then I can repeatedly tell them to do things until I get some kind of evidence that they might be following somebody else. Right? Which means the next time I want to prepare for slot number 2, I don't need to prepare. I can just send out an accept message, and if I got unlucky and somebody else had prepared something, I would learn about it, my thing wouldn't get accepted, and then I could decide what to do. So, let's see, skip phase 1 when possible. Right? So every new proposer runs phase 1, and then does phase 2 as many times as they can get away with, until somebody else with a bigger number does phase 1. And precisely because of that, if we don't have a mostly sticky leader, this optimization almost never happens. Right? You win when you can skip phase 1. You can skip phase 1 if the same person is always doing accepts. In order to make it the case that it's really unlikely that more than one person is doing accepts, we also rub on a completely independent leader election protocol. That has nothing to do with the Paxos protocol. It's just some other protocol we run to try and make it really unlikely that somebody out here is going to do a prepare. Right? Everybody with me? Anything else? Well, actually, there's quite a bit more that we're not going to look at in this class. Well, one thing that's frustrating that we talked about a little bit is, well, let's take this exact scenario, put in it here. Okay? So somebody said prepare 1.1, and then they said accept 1.1 for slot 0, the value, I don't know, x. And I know that x was accepted, right? Because I got to a majority of acceptors. These people have all replied 1.1. Okay, so let me ask you something. Well, actually, let me say P1, A1, A2, A3. And we can imagine that these all can be proposers too. So I said that that x was chosen. Is that a true statement or am I wrong? Was x chosen in this execution?
Yeah.
Yeah, okay. Who knows that x was chosen?
P1, A1, A2.
Somebody said P1, A1, A2. Well, I believe that P1 knows. And in fact, P1 knows exactly here. It's like the commit point in primary backups, right? The very moment that P1 hears from a majority of acceptors that the very ballot that they put out was the thing that was accepted, they know. Does A1 know? It knows that it accepted something. But it also knows that it'll accept the highest thing it ever saw no matter what. And it also knows that it might change its mind, right? Because in a different world, this acceptor might have crashed here before sending out this message. X never gets accepted by anybody but A1. Somebody else comes along, suggests Y, and gets Y accepted. So in the end, in the fullness of time, A1 may need to change its mind. Now it thinks that it's X. Later it may need to decide Y, because Y comes along with a higher value. That can happen. Right? So A1 doesn't know. And by the same argument, A2 doesn't know. So wait a minute. In Paxos, the only person who knows if something was accepted is the person who proposed it. How could anyone ever know? How could anyone else ever find out what values were chosen? That's absolutely right. So in the protocol that we've studied, there's exactly one way for A1 to find out what was chosen. And that is to pick a new number, let's say prepare 7.1, and send the message out to the other acceptors. And if something was chosen, surely one of these replies will have the chosen thing. So basically, the way that you can find out what was chosen is you come into the world and try to propose your own thing, and if something was chosen, you don't get to propose your own thing, you have to propose their thing. And when you're done succeeding getting that thing accepted that was already accepted, now you know that it was chosen. But that's stupid, right? Because if you do that, you're going to lose your sticky leader. If you do that, you're doing 2 rounds of communication. So in addition to all this other stuff, this is what Osterhouse calls like full disclosure. Practical implementation of Paxos also needs auxiliary protocols similar to anti-entropy in quorum systems that have acceptors periodically talk to each other and tell each other what the truth is. Right? So that's like, whew. So you're like, okay, cool. So you want a totally ordered mod, right? First thing you do is study Synod for like 5-6 years. Make sure you understand it. Make sure you understand how to implement it. Cool, now you understand Synod. Maybe you've proven it to be correct. Cool. Now all you need to do is like 27 little retrofits and optimizations that are scattered throughout the literature, written in different formalisms, blah, blah, blah. And when you've read all 300 of those papers, there's even a paper called like Paxos for System Builders. How the fuck do you actually implement Paxos from a non-academic point of view. Then finally you have something that maybe works. The problem is, the thing that was proven correct is this thing, not this kitchen sink. God knows if when you're done applying all those optimizations, you have a protocol that solves consensus. And this is all just to say, and I don't want to spend a lot of time on this, but I'm not the only one to be frustrated, both by sort of the apparent complexity of Paxos to a first approximation. When I first studied Citadel, I was like, that protocol's crazy, doesn't make any sense. And then little by little, I convinced myself that it did make sense. But I still think it's crazy that to turn it into something useful, you have to go into this realm of unknowns. So the idea behind Raft was we want a consensus protocol, but not a consensus protocol that's layered up from first principles so that all of the sub-protocols make academic sense, but rather a protocol that was designed from the ground up to implement a totally ordered block. So from the very beginning, Raft is designed to include sticky leader election that's likely to terminate, to include indexes on all the things, to include single phase optimizations and so on and so forth. Right? So there's not much to say about Raft except to say it is made out of the same building blocks that we studied in our first Paxos lecture. It involves a two-phase protocol with reconnaissance. It involves unique monotonically increasing sequence numbers generated by the proposing entities. It involves majority rule. So it has all the same building blocks, but they're constructed in such a way that it's supposed to be easier for you to see all the way to the composed system. And the authors of Raft call it an understandable consensus algorithm. In fact, the title of the paper is In Search of an Understandable Consensus Algorithm. But understandable is a little weird because it sort of means two things. Or at least when the authors use it, it appears to mean two things. On the surface, there's like the shallow meaning that's like, when I print out this paper, I understand how to implement the protocol. Which I think is like what a lot of people complain about Paxos. It's like, I think I understand why it works. I just don't understand how to build it. There's like, I understand how to implement the protocol. And I would argue, maybe I'm going out on a limb here, but I would argue that it's this version of understandable that has made Raft so popular. Like, Raft is really popular in the industrial world. Nowadays, when people implement a consensus algorithm, they tend to implement Raft. Why? I think because it's easier to print out the paper and just get hacked. It's easier to understand how to begin coding the friggin' thing up. But of course, sometimes when we talk about the understandability of an algorithm, we're trying to understand like why it works. Like, why does it solve consensus? Why does there not exist an execution under some of everything that falls to the channels to solve consensus? And that's like super hard. And I don't think that Raft, and maybe I'll share the paper because you might be interested. I don't think Raft really delivers on this promise. I don't think it's any easier to convince myself that Raft is correct. And this is kind of why I gave our guest speaker such a hard time, because I think that, like, in practice, most implementations of consensus algorithms are not. So we should tread carefully, and we should really understand. If I had to choose which of these versions of do I understand it, maybe it's because I'm an academic, I would choose number 2. Like, I want to implement the algorithm that I understand why it's right, not I understand how to begin C++ing it up. All right, so that's just opinion.
Question?
Okay, yeah.
So if Raft and Paxos are the same, what's the difference between the two?
I mean, they're different protocols. I mean, what do you mean by the same? So like
You said they're made from the same building blocks?
Yeah,
and
yeah. Like I said, they
use the
both
same-
involve voting, counting majorities, two-phase protocols, sequence numbers. They're made out of those pieces, but they make different decisions. The code is structured differently. One really obvious example is like, they're like, leader election is going to be part of the damn protocol. The way Raft works is first you figure out who's the leader, then the leader does things. sometimes there's 2 leaders, so you have to be careful. As opposed to being like, let's come up with this protocol that sort of everybody can play every role. Oh, by the way, that'll never work in practice. Let's elect a leader, but I'm not going to tell you how to elect a leader. That's an exercise for the reader. Raft is like, first, implement leader election in exactly this way. And then when you're done with that, then layer this other thing on top of it. So it's very much like a layered discussion, but you know, the protocols are, I mean, they're, I think it is an interesting philosophical question. Like, obviously, I have a protocol, there's an infinite number of implementations of the protocol. All those implementations are different, but it's tempting to say they're not protocol level different, they're implementation level different. But at some point you imagine, I have this protocol. I actually have a paper about this in Hot Time 2017, where it's sort of like implementation 1, and you're like, oh, I have this little optimization. And that's not like a protocol level change, so I don't need to like specify it again or anything. I just go to implementation. So over the protocol's lifetime, you specify it maybe once, you port the specification to an implementation, then you start like editing the implementation. Now one imagines that at some point, we've crossed over and like, this is actually protocol prime, buddy, and you actually need to re-verify that. But how the hell do you know which of these like little incremental changes is tantamount to a protocol level change, as opposed to like a little optimization and who cares? When do you need to, as you're doing this thing that anybody does, as you find bugs and fix them, or find faster ways to do things, when do you need to sort of backport and re-verify, or prove something new, and when can you just keep going on this? It's hard. But I mean, it's to your point, like, at some point, like exactly what magnitude of change constitutes like a protocol level change versus an implementation level change is a somewhat philosophical matter, but there isn't really maybe there isn't a correct answer to that. If you're interested in that paper, it's called Growing a Protocol, which is a reference to this really famous Guy Steele talk, Growing a Language, it was still in 98 or something. Anyway, let's talk about a really fearsome impossibility result. But before we do, let's refresh the models that we're operating in when we talk about a protocol like Paxos. What kind of network model do we assume when we're implementing and talking about Paxos?
Async.
It's the async model, right? Where we're not making any assumptions about upper bounds on communication latency. It's in the async model that all the fun reordering stuff that makes protocol development hard happens. Right? And what about the fault or failure model? Where do we like to live for stuff like Paxos? The omission model, that's right. Why not the Byzantine model? That's too fucking hard, right? I mean, like, sure, it would be great if we could solve it in the Byzantine model, but not in 1.8. Right? And then I think, as I made this argument, I don't know if you all remember, that like, corporations operating code in their own data centers have this bedtime story, which I think is pretty reasonable, which is that mostly only omission faults happen within our administrative control, and the small number of technically Byzantine faults that do happen commonly in the data center, corruption in particular, we can detect and fix by dropping, turning that Byzantine fault into an omission fault. So they argue, you know what, if we just live in the omission model, we pretty much deal with everything. Okay, so FLP result states, I'm just going to write it out. And then async distributed system I'll kind of underline each of these things to make sure we're clear on what it means. Any deterministic protocol that solves consensus distributed system, oh, I should hang on, in which at least one process may fail by crashing solves consensus has executions that do not what? Terminate. Or you may have heard the following gloss. Consensus is impossible. I think it's worth trying to understand how these two statements of very different lengths relate to each other. So, do you think that consensus is impossible? It depends what you mean, right? I mean, I think like it's certainly not a very satisfying definition because like consensus is this thing that I hope I have convinced you we frequently need in distributed systems. So consensus is a thing that you need sometimes. It's also a thing that you do all the time. It's impossible. Yeah.
So I would say that it's not impossible in the sense that consensus is a thing that can never happen. But it is impossible in the sense that you cannot guarantee that consensus will happen.
Yeah, that's exactly right. I mean, consensus is likely as hell. But the point is it's impossible because I cannot guarantee that in every execution it is achieved. All you have to do to establish a gloss like this is to show that if I have a protocol, let's call it P, what do you have to do? Well, I have to assume nothing about P except what's in the definition here. I have to assume that P operates in a distributed system, so it passes messages. I have to assume that in that distributed system, messages I can't say anything about when they need to be delivered. I have to assume that P is deterministic in the sense that given the same inputs, it will always produce the same output. I have to assume that processes can crash. If I make only those assumptions, and I prove that, imagine we had a protocol P about which those things. If I can take us to a place where, and imagine that P solves consensus. If I, by assuming those things about P and the fact that it solves consensus, I can prove a contradiction, I have proven that no P could ever exist that solves consensus under those assumptions because I didn't assume anything about P. Right now, if I start talking about P and start talking about proposers and acceptors, now the proof goes out the window, right? Because now I'm assuming some things about P. Now I've just proven that a protocol that uses the proposers and acceptors might not terminate, right? The trick is assuming nothing about P, but what's in the definition. Yeah?
Could you move the floor down?
Sure. Now the way that they end up, I'll just give like the tiniest proof sketch, just to give you a roadmap if you want to go look at the proof yourself. We sort of are going to have like a base case that they're going to prove and an inductive case. And the base case is they're going to establish that any protocol P, assuming nothing about P except all those things over there, has a, they use this term, bivalent, I'll explain what it means in a second, initial state. And the proof of this lemma is just amazing. So I'm not going to mention it because I'll just freak out and spend the whole day talking about it. What does bivalent mean? Bivalent means I have a consensus algorithm C. You imagine that sometimes in a particular execution of C, let me say something else. They're going to do this, going to simplify things. So some of the simplifying assumptions, let's see, where should I write this? Simplifying assumptions. The first one is that we're just going to be deciding on one of two things, 0 or 1. It's a Boolean valued consensus problem. There's a question that came up, it's not here, there's a question that came up, was like, is consensus easier if we place constraints on the values that you're choosing? It turns out that no. Because if all you're deciding is true or false, the impossibility result still holds. So it follows that if you're deciding more complicated things like who's the president, it's going to hold. They assume that only one process can crash. So they're not in the omission model. They're not even in the crash model. They're in like the crash footnote, oh, only one crash. And they're still able to prove impossibility, which means that this FLP definitely holds in the omission model. Does everybody buy that? The argument that if something, you can't do it in the crash model, you definitely can't do it in the omission model. And if you can't do it with only one process can crash, you definitely can't do it when k processes can crash, right? So despite these simplifying assumptions, we get this impossibility result. Okay, now, a consensus algorithm, you imagine that sometimes, at some particular point in its execution, it doesn't know yet whether it's going to decide 0 or 1. We need to send a few more messages, then we'll figure it out. This is what you call a bivalent state. I can go either way, I don't know, I haven't decided, I'm undecided, I like them both. You know? Or, maybe like you've decided, so you're univalent. Now we know that the protocol might have to make a few more steps, but it's a foregone conclusion now. This protocol is going to decide 1. Okay? Okay, so the way that they're going to prove the impossibility result is they say, first we're going to prove that for any protocol K, there are bivalent initial states. That before anybody sends any messages, the final consensus decision is not, people are going to have to send messages. And like the trick involves like, should I even say this? It ends up coming down to, let's say that every initial state was univalent. Let's say that there were no bivalent initial states. Then there would be, you know what, no, I'm not going to get into this, too hard. The point is they prove that, assuming nothing about P, there must be at least one initial state. And by initial state, I mean we have all these gadgets that are trying to solve consensus, and they all have the inputs that they want to do. So this guy says, I want 0. This guy says, I want 1. This guy says, I want 1. And this guy says, I want 0. And the bottom line is, we don't care what they decide, but they all have to decide the same thing. This is like an initial state. The intent of everybody going into it. And so some initial states, I can just look at the initial states and say, this thing's going to decide 1. And some, I look at them, I'm like, I don't know, because depending on who fails, I don't know. That make sense? So, okay, at least one initial, bivalent state. And then we have your induction case, which says, from a bivalent state, it is always possible to deliver a message and end in a bivalent state. Right? And the rest is just a victory lap, right? Because they say, well, okay, so there is this bivalent initial state B. And although there might be many transitions we could take out of B where we deliver messages and go into some univalent state and life is good, for any P, it's possible to find ourselves in B as a consequence of our initial states. And there always exists at least one transition in which we do work and we end up back in the bivalent state. Which means there's an execution in which we start in the bivalent state and we stay in the bivalent state. And this is not a deadlock situation. We keep delivering fucking messages. We're like doing computation. We're just not getting anywhere. Right? And I think I have an intuition for this, right? Which is that, can I do this? Can I do this? Let's see. It would be so cool if we lived in a world in which the more messages we passed, the strictly more information we had. Right? In which, like, the more we share with our peers, the more collective knowledge we all have. Knowledge monotonically increases. And if that were true, then you could always just define, okay, there's this threshold where the knowledge needs to be, and we just need to get there. And the way we get there is by sending more messages. Some of the messages don't make it, but eventually we goddamn well that isn't even good because it's monotonic, right? So we eventually get to that threshold, and we know once we get to that threshold, we'll never come back. Like, we would like to have that property. The more you know, the more you know. The more we talk, the more we all know. It would appear that that property of monotonic growth of knowledge is at odds with the property of fault tolerance. In a world in which there's uncertainty about who's alive or dead, sometimes, as you get more information, you know less. Sometimes you're making progress in the state machine. I'm at state, this state. I get to this new state, and I get to this new state, and then suddenly I get some new piece of information that's like, ah, crap. I'm back to that like first state again. When would that happen? Well, we studied one example in excruciating detail in this class, right? Which it's about the problem of failure detection, right? So I have a consensus system, and it would be great if everybody participated in the consensus system. So it would be great if everybody stayed up. So please, everybody stay up, send messages. But you need your protocol to be fault tolerant. So some of the nodes will occasionally, in a consensus protocol, need to make a decision that one or more of the other nodes are gone and they're never coming back, and make progress without them, right? If you didn't do that, you wouldn't be fault tolerant. So any P that solves consensus, if at least one process can crash, has to have a sensible plan B for when a process crashes. The thing is, a process crashing is not positive information. It's just the absence of a message, right? I think you're crashed because I didn't hear from you when I heard. So let's imagine this world in which we make progress, we get to a place, and now we're like, gee whiz, if I heard back from this one process, we would know what to do. We would go to the good place, But I'm going to decide that I'm never going to hear from that process. So now state S prime prime is what I do when process P is never going to come back, or process Q is never going to come back. And maybe there's a way to get to the good place from there too. So you're like, okay, good. The reason that I went from this state to this state was because there was a message, let's call it M question mark, that I did not receive, right? Had I received M question mark, I would have known that the guy was up. I would have gotten to the good place, but I didn't receive it. So I go to this new place, S prime prime, and I'm trying to find my way, maybe through some intermediate states to the good place. And then I get M question mark, which means I have to revise my knowledge of the world. Does that make sense? So in some sense, like, these two things that you would like. The more we talk, the more we know, until we know enough to take action. Versus, we have to be able to make progress even if somebody dies and never comes back and we have no way of knowing if they're really dead. Are fundamentally at odds with each other. Monotonic growth of knowledge and fault tolerance don't play nice together. I think that's true. Okay, questions about FLP? And so I won't say too much more about it, except I will share the paper with you and say that, like, this impossibility result really, I don't know, man, it really framed a lot of the academic discussion around consensus. Like, to give you a little bit of a history lesson, like, this was, what was FLP? Lindsay, do you know when FLP was, 97? Like the 90s, late 90s. No, it wasn't the late 90s. It was like the 80s. It must have been the 80s. Because Leslie Campbell was like 95. All right, well, I should have known this before I started lecturing on it. But let's just say it's the 80s. So it was like early work, people established that in the omission model, in the async model, that it has to do not just with the fact that the process can crash, but the fact that there's uncertainty around time. Right? If you take one of those away, everything becomes easy. And people decided, well, since it's impossible to do a useful thing, let's stop studying consensus in the omission model. Let's go back to studying, or in the async model rather. Let's go back to studying consensus in the sync model. And so then there was like a decade of research after FLP in which researchers figured it was too hard of a problem, and they studied simpler models where they thought they could prove that you could achieve something useful. And then in about 1995, Lamport came up